Hello, in this week's reading we looked at the electric fields of dipoles and some special cases, as well as the electric interactions with neutral matter. From a chemistry course I took a couple of years ago, I was familiar with the term dipole, as when examining chemical bonds, one of the interactions to look for were dipole-dipole forces. From last week, I was also familiar with the electric field calculations and the use of superposition required to calculate the electric field of a dipole. Okay, so first of all we looked at what a dipole actually is. It's 2 point charges of equal magnitude or opposite sign separated by some distance. To calculate the electric field of a dipole, we first calculate the electric field of each point charge at a point and superpose to calculate the dipole's electric field at that point. We're now moving on to the content which was new for me this week. We looked at the vector P, or the dipole moment. The vector quantity has a magnitude of QS, where Q is the charge of the point charges in the dipole, and S is the distance which separates them. The dipole moment operates along the axis of the dipole and is directed from the negative charge to the positive charge. Here, we should also note that the vector R points from the centre of the dipole to the observation location at R- and R+, point to the observation location from the negative point charge and positive point charge respectively. Next, we derived an equation for calculating the electric field of a dipole if the observation location is on the axis of the dipole, which we can see here. We looked at a more specific case of having an observation location on the axis, which is when S is comparably very small when compared to R. By letting S equal 0, we can determine that in this new case, we can use the formula seen here. Following this, we looked at another special case for calculating a dipole's electric field, which is when the observed location is perpendicular to the axis of the dipole. In this case, the magnitudes of R+ and R- are equal and have a magnitude of the square root of the magnitude of R squared summed with S over 2 squared. Using the theta indicated in this diagram, we can also work out that the cosine theta is equal to half S over this previous value. After some substitution, we reach this equation for the value of the electric field of the dipole when the observation location is perpendicular. It is worth noting that it operates in the direction of minus p hat and therefore is parallel but opposite to the direction of the dipole moment. Much like the case when the observation location was parallel, we then looked at a more specific case of the observation location being perpendicular, which was when S is comparably small when compared to R. Here, we can again set S to equal 0 and reach this equation. Comparing this one to the equation we reached in the parallel case, with R being much greater than S, we can see that E dipole perpendicular has half the magnitude of E dipole on axis. Lastly, we looked at electric interactions with neutral matter. Matter is neutral when it has a net charge of 0. This doesn't mean that said matter can't have an electric interaction, however. For example, a dipole has net charge 0, but creates an electric field. We looked at an example of a permanent dipole, a water molecule. We also looked at induced dipoles, another topic familiar from chemistry. However, what we covered this week was new to me. First, the dipole moment is equal to alpha E external, where alpha is the polarizability of a molecule, and also that the dipole moment will act in the direction of E external. Of everything we covered this week, I think the thing which gave me the most difficulty was wrapping my head around induced dipoles, because I was trying to think about how the dipole needing equal charge at each point would affect it. But after looking at the examples on the electric polarization page on the physics book, I feel I have a better understanding now. As a CS major, something I was thinking about while watching this week's lecture was how it would be interesting to create a program which could display the electric field of a dipole. While most points wouldn't fall on the axis or perpendicular to the dipole, in those cases you could use the equations we've seen this week, and otherwise you just have to perform a few additional calculations. But thank you very much for listening.